All right, today we're going to dive into a technology that sounds like it's straight out of science fiction. Optical Coherence Tomography, or OCT. But this isn't just about some fancy machine. Nope, this is the story of a brilliant evolution. How a clever physics idea grew into a total game-changer in eye care.
So let's just start with a question that honestly is pretty mind-bending. How can a doctor see the tiny microscopic layers inside your retina and get a perfect, high-res picture without ever making a single cut? I mean, think about that for a second. That's the incredible problem that OCT was built to solve.
And the answer is optical coherence tomography. Yeah, I know, it's a mouthful, but the core idea is actually really simple. The absolute best way to get your head around it is to think of it as an optical ultrasound. You know how ultrasound uses sound waves to see inside you? Well, OCT does the same thing, but it uses light waves to map out the back of your eye with unbelievable precision.
So how in the world does that work? How can you use light to measure depth? Well, the secret sauce behind the whole thing is a physics principle called low-coherence interferometry. Sounds super complex, I know, but the basic idea is just elegant.
Okay, so picture this. The machine starts with a single beam of light. That beam hits a splitter, and just like it sounds, it splits the light into two paths. One part, we call it the sample arm, heads straight into the patient's eye. The other half, the reference arm, is sent over to a perfectly placed mirror. Now this is where the magic really happens. The light from the eye bounces back. The light from the mirror bounces back, and when those two beams meet up again, they create something called an interference pattern. But here's the catch, and this is everything. They only create that detectable signal if the time they spent traveling their separate paths is exactly the same, down to a fraction of a wavelength. And that right there is the key to measuring distance, which means we can measure depth inside the eye.
The very first version of this technology, which we call Time-Domain OCT, had this really clever but very mechanical way of putting that principle to work. Let's break down how they did it.
Okay, so in this old school method, that reference mirror isn't just sitting there. No, it's physically moving, scanning back and forth. At each and every tiny position it stops, its travel distance perfectly matches the light bouncing back from one single specific layer deep inside the retina. The machine gets a signal, records it for that one layer, then the mirror inches forward and it does it all over again for the next layer. It literally builds the final image piece by piece, one depth at a time.
The best way to picture this is to imagine a super meticulous construction worker with a tape measure. They measure one spot, write down the number, pull the tape back, measure the next spot, write it down. You get a really accurate set of measurements for sure, but man, is it slow. And right there, you see the problem, right? Having a physical moving part creates some pretty big bottlenecks. The process was just slow, and because it was slow, the images weren't as high-res as they could be. Plus, you have to ask a patient to stay perfectly still for longer, which means any tiny little eye movement could blur the whole picture.
But then, things got a lot faster. A genuine revolution in speed and power came along, and it was called Spectral-Domain OCT. This changed everything.
So what was the big game-changing idea? It was so simple, yet so brilliant. They just got rid of the moving part. That's it. In Spectral-Domain OCT, the reference mirror is totally stationary. And that one simple change had absolutely massive consequences. You're probably asking, okay, if the mirror isn't moving, how does it measure all the different depths? Well, instead of listening for one tiny signal at a time, the new system just grabs all of the reflected light from all of the retinal layers all at the same time. What you get is this jumbled up mix of light waves, a complex pattern that basically holds the secret code for all the depth information at once.
So how do you crack that code? With math. It's a bit of mathematical wizardry called a Fourier transformation. You can think of it like a super powerful decoder ring. It takes that jumbled up light signal and in one single computational step, it unscrambles everything and rebuilds the entire beautiful cross-sectional image of the retina. No moving parts, just pure math.
So let's go back to our analogies. If the old way was our careful worker with a tape measure, this new way, well, it's like a crazy futuristic camera that takes one single snapshot and instantly knows how far away every single object in the room is. It's not just a little better, it's a whole different league. Okay, so let's actually put these two technologies head to head. You really get a sense of just how massive this leap from a mechanical fix to a mathematical one really was when you see the specs. I mean, just look at this. It's crystal clear. You go from a moving mirror to a stationary one. From measuring one depth at a time to capturing all of them simultaneously. And what does that all add up to?
It's dramatically faster, the images have much higher resolution, and all of a sudden, creating a full 3D map of the eye isn't a science project anymore. It's something a doctor can do right there in the clinic. And if you had to boil it all down to one single, most important factor, this is it right here: the speed. The increase wasn't just a small step up. We're talking a night and day difference, a quantum leap. And that incredible speed is the key that unlocks everything else.
So what does all that speed actually get the doctor in the real world? It means they can take thousands of scans in just a few seconds, creating these incredibly dense data sets. And that gives you those crystal clear, high-definition images, and it allows the computer to stitch them all together into amazing 3D models of a patient's eye anatomy.
Now, all of this physics and engineering is fascinating stuff. But the real story here is the impact. Why does this leap from a moving mirror to a math equation actually matter? It matters because it helps save people's eyesight.
With the power of Spectral-Domain OCT, doctors can now see things they could only dream of before. They can see the individual layers of the retina, check the health of the actual photoreceptor cells that let you see, and spot tiny pockets of fluid that are a huge red flag for disease. This has become an absolutely essential tool for managing the biggest causes of blindness, things like macular degeneration, diabetic eye disease, and glaucoma.
So, at the end of the day, if you take just one thing away from all this, let it be this: the incredible evolution of OCT really boils down to replacing a physical, moving part with a much more elegant and unbelievably more efficient mathematical solution. It's the perfect story of how progress so often means just finding a smarter, faster way to get information.
And that really leaves us with this final thought, which just captures the beauty of it all so perfectly. It's about taking something we can't even see, these interference patterns of light, and using the pure language of mathematics to turn them into a detailed, life-saving map of living human tissue. It's a true marvel of applied physics meeting medicine.